This problem is taking a look at one where we're given the information in context. So in this case, we have a car that is purchased new for $20,000, and it is then found to be worth $12,000 just 1 year later. And we're going to write an equation to represent the value of the car. Well, the first thing I want you to notice is that since we're talking about how this is changing over time and how the car value is going to change not by a set amount each year, but actually more like a percent each year, that when it is decreasing in value, it's doing so according to an exponential model. We actually call this exponential decay. And that just means that the value is going down according to the exponential model over time. But since it is over time, I don't really want to use this equation in terms of y and x because we're talking about a real situation here. And so I'm going to choose different letters here. I'm actually going to choose to use a and t instead of x and y, where a would represent the amount, that is like the value of the car, and t would represent time, in this case measured in years. I particularly chose these two letters because these are fairly typical when used in financial applications like this. Now, in the previous problems we've done like this, where we've had to write the exponential equations ourselves, we've always been given 2 points. Well, we actually have been here as well. Do you see what the actual points are? Like write 2 coordinate pairs of points. Well, let's take a look at this 20,000. That 20,000 would be the final value. That's like the final amount, right? So that'd be like 20,000 there. At what time was it worth 20,000? How many years had elapsed? Really none. And then we're told that 12,000 happens after we've had this car for 1 year. And so those are really the 2 points that we're going to be working with in this problem. So now that we know that, we can go ahead and go through that same process that we've seen with the other ones, where we write the 2 equations, including the x and y values from each of those 2 points. But you'll notice something kind of cool happens in this case, because I can simplify this first one down a little bit because it has b to the 0 in it. And remember that anything to the power of 0 equals 1. And so here the 20,000 then equals a, because a times 1, and a times 1 of course is just a. And so we know what our a value is, our little a value. And yes, lowercase a is different than uppercase a when we're writing these equations. They mean different things. So already I know what a is. I don't even have to do any extra work, and I know what a is. Great, let's use that. So in the second equation, I can also simplify that just a little bit, not really too much though, because there all I can do is say that b to the power of 1 is just b. But that is at least simpler than seeing that power of 1 in there. But now what I'm going to do is I'm going to take this value of a that I found from this first equation, and I'm going to plug that in for a in the second equation. So let's go ahead and do that there. I'm going to have 12,000 equals 20,000 times b. Notice, in order to get b now, all I have to do is divide both sides by that 20,000. And when I do that, I end up getting 0.6 equal to b. So we need to figure out a, and we need to figure out b. We did it. That's all we actually have to find in order to be able to now write our equation of a equals the a value, which is 20,000, times my b value, which is 0.6 to the power of t. And we're done. That is our equation. And this is also a great example of some little shortcuts that we can start looking for when writing these equations as well. Because you'll notice that if we are given the value at 0, we already know that that's our a value. And so then what you can see then is that in this form of equation, your y-intercept is the a value, which can be a little bit of a mind bend compared to like linear and where the y-intercept shows there. It's a different kind of graph, so the y-intercept shows up in a different way.